Video course on statistics. From basics to advanced subjects. Dr. Yahya El-Maghazi. Professor Emeritus at Auburn University, Alabama, USA. Former Dean of Science, Technology, Math, Engineering at Ocean County College, New Jersey. A visiting professor at a number of universities including Rowan University, Keene University, and Montclair University, New Jersey, USA.
Dr. Yahya El-Maghazi is the founder and the president of L-Learning LLC, a consulting education organization. You can order a complete set of the course with all video sessions, slideshows, PDF file of the course, test bank, and data bank by visiting Amazon.com.
Probability Analysis. Part 2. Probability distributions of discrete variables.
In this section, we will move with the subject of probability into where probability is best used in the real world. And that is the subject of probability distributions. We will discuss discrete probability distributions or probability distributions for discrete variables, and probability distributions for continuous variables, and we will provide you some examples to show you how we can use these distributions in actual real-life applications. In addition, we will use Excel Microsoft to demonstrate how we construct or develop a probability distribution and how we find the values of probability obtained from probability distributions if we need to do so. Now let us go to the slides and start our session on what is a probability distribution. Well, a probability distribution, early on in chapter 3 or in the 3rd or 4th sessions, we discussed histograms. And we said that a histogram is a two-dimensional graph. X-axis represent the variable value, and the y-axis represent the frequency or the number of observations, if we recall. We also moved to the so-called relative frequency distribution, which was the frequency of each class or each value divided by the total frequency. Well, relative frequency is as close as it can get to what we call now a probability distribution. It's a two-dimensional graph, as you can see here. The horizontal axis is the variable and the vertical axis is the probability. And probability here is a fraction, as we mentioned. Recall in the previous session we said probability will range from 0 to 1. So any value in this axis here will have to be a fraction or a value from 0 to 1. A plot that allows us to determine the chance of some outcomes and make decisions under certain conditions is generally called probability distributions. Precisely, a probability distribution, as I mentioned, is a relative frequency distribution of all possible outcomes of an experiment. To construct a probability distribution, we need to know all the possible outcomes of an experiment. We need to know the possible patterns of the variable under consideration, because it may actually follow certain patterns that we know from past experience. We also need to know the parameters controlling these patterns. So these are the 3 P's that are required in order to construct or develop a probability distribution. Let's see the different types of probability distributions. Well, the different types of probability distributions correspond to the different types of variables. In this regard, we have 2 types of variables. We have discrete variables and we have continuous variables. Discrete variables are variables whose sample spaces are set of discrete points, 0, 1, 2, 3, and so on. When we toss a coin, we have discrete outcomes, head or tail. When we inspect a product, we have discrete outcomes, pass or fail. When we're counting the number of defects, we say 5 defects, 6 defects, 8 defects, but we never say 5.5. That's what we mean by discrete variables. Continuous variables, on the other hand, these variables can take any value in a specified interval falling within their plausible ranges. The diameter of a fine metal rod, for example, can be 40, can be 40.25, can be 40.75, can be 41. Human weights can be 120 pounds, 155, 165.8. You can see the continuity. Students' grades can be 75, 75.8, 76, 80, 80.5. So this is what we mean by continuous variables. For each one of these types of variables, there is specified or probability distributions that are suitable for the type of variables. So as a result, we have probability distribution of discrete variables, and we have probability distributions of continuous variables. Now notice the difference in the shape here. Probability distributions of discrete variables are described by lines or needles, as you can see. So the x-axis are discrete values, 0, 1, 2, 3, 4, and so on. And since there are no numbers in between, there are no decimals, there are no fractions, then each number is represented by a frequency or relative frequency or probability that's represented graphically by a needle or a straight line. While in continuous variables, since continuous variable can take on any value, then that takes us back to a histogram, and as you can see here, these variables are represented by bars, or the frequency are represented by bars, and these are continuous bars, implying that we are dealing with a probability distribution of continuous variables. Some of the common examples of discrete or probability distribution of discrete variables are the binomial distribution and Poisson distribution. We will discuss these shortly. And some of the common continuous variable probability distributions are the uniform distribution and the normal distributions, which will be discussed in later sessions. So let's start by the probability distributions of discrete variables. And again, as a reminder, we describe probability distributions of discrete variables by needles. The horizontal axis here is the discrete values, 0, 1, 2, 3. It cannot be 2.5 or 4.6. And the vertical axis is the probability corresponding to these x values. What we just described is the so-called binomial distribution. And let's see how the binomial distribution is obtained in practice. In previous sessions, we discussed the experiment of tossing a coin twice, or tossing 2 coins at once. And we said that here are all the possibilities. We may get in the first toss a head or tail. In the second toss, if you get a head in the first, then the second toss may be head or tail. You can see the tree diagram describing that now. If you get a tail in the first toss, in the second one you may get a head or tail. So we end up with 1, 2, 3, 4 final outcomes: head, 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 tail, tail, head, and tail, tail. These are all the possible outcomes of tossing a coin twice or tossing 2 coins at once. Let us put these into numbers now. If our interest is the head, then in this case, if we look at the first outcome, this is a 2 head showing. In the second case, it's only 1 head because it's head and tail. In the third case, it's also 1 head because it's tail and head. And in the fourth outcome, we have no heads because it's tail and tail. So these are the values of x. And as you can see here, we're dealing with discrete values, either 0 or 1 or 2. Now, if I look at the probability associated with these outcomes, since we have total of 4 outcomes, then any one of these outcomes will have a probability of 1 over 4. That's the classic law of probability. So we have here 1/4 all the way to the end. And notice if you add up these, you will have a sum of 1, which is the second rule of probability. The sum of all probabilities is 1. So now we have a simple table where we have the variable values 0, 1, 2, and the probability. Now, speaking of 0, here it is. 0 has a probability of 1/4, so the probability will be 1/4. Speaking of 1, we have 1 shown in this outcome, H and T, and we have another one shown in this outcome, T and H, and by the rule of addition, then we have to add the 1/4 plus 1/4, and that gives us 1/2. That's why at 1, the probability is 1/2. Now at 2, since we only have 1 outcome, the probability is 1/4. This simple frequency table, or we can call it probability table here, where we have the variables and the probabilities, is what leads to the so-called binomial distribution. And as you can see here, the horizontal axis has the 3 variable values, the 0 and the 1 and 2. Here is 0, 1, and 2. And the vertical axis represent the probability. And at 0 we have 1/4, at 1 we have 1/2, and at 2 we have 1/4. So we just constructed a simple binomial distribution. Notice it's a symmetrical distribution, and that's what you will always get when the probability of event is 1/2, such as the case of a coin tossing. If we want to get the mean value of this distribution, then all what we have to do is to sum up the variable values times the probability. So the products of the variable times probability will give us the average value. You see here mu equal the sum of x px. That's the sum of this multiplied by this, plus this multiplied by this, plus this multiplied by this. You can see we have 0 times 0.25, or 1/4, 1 times 0.5, 2 times 0.25, and that will give us 1, meaning that the average value of this particular binomial distribution, which reflects or demonstrates the tossing of 2 coins, is 1. If we look at the standard deviation, the equation is very simple. This is, by the way, derived from the previous discussion of the weighted mean of frequency data, or the standard deviation of weighted data. Sigma here is the square root, or the standard deviation square root of sigma x squared px minus mu square. So if we square each x and multiply by the probability, and we get the sum of these minus the mu square, we will get the standard deviation of the binomial distribution. That leads us to the binomial function. The binomial function is looking as we see here. Px, or the probability of x, is a function of x for a given n. And what you see here is the combination symbol or term that we used before, that you can say ncx, or n combination x, times p to the power x times 1 minus p to the power n minus x. Or px will be equal to, if we want to resolve this term here, it's factorial n divided by factorial x times factorial n minus x. All of this is time px and 1 minus p n minus x, or we can replace the 1 minus p by q. Now notice that q is equal 1 minus p, and the variable values here can either be 0, 1, 2, 3, 4, and so on. That's what would lead us to this distribution. So in order to construct this distribution, we have to actually use this function, as we will see by example very shortly. The key here is that the parameters of a binomial distribution is n and p. If we know n and p, then we definitely know how to construct a binomial distribution. we need to first understand the different characteristics of a binomial function. Knowledge of these characteristics and the parameters of the distribution will help us using the distribution in simulation applications, as we will discuss later on. With that, let us go to the slides and see how we're going to use the binomial distribution by first introducing the different characteristics of the distribution. We said before that the binomial function will look something like this, where the key parameters in this function is n and p. These are the two most important parameters, and indeed, in order to develop a binomial function or a binomial probability distribution, you need the n and p. We also said that this is a discrete variable probability distribution, meaning the values of x have to be discrete, as we can see here, 0, 1, 2, and so on. We now know the shape of the binomial distribution, roughly. It doesn't have to be symmetrical, but we know that it deals with discrete values and it's represented by needles or straight lines, as we said before. We also learned that the two parameters that describe this distribution is the sample size n, or the number of units inspected, and the probability of the event. Very good. We also learned that the mean of the binomial distribution can be simply determined by n times p. So if I know the number of units inspected and I know the probability, then the product of n p will give us the mean of the distribution. The variance of the distribution, on the other hand, can easily be calculated from npq, where n is the number of units inspected, p is the probability, and q is 1 minus p, or 1 minus the probability of the event that we are addressing. The binomial distribution is the most appropriate probability distribution for sampling from an infinitely large population. So the larger the population, the more suitable and appropriate the binomial distribution, where p represent the fraction of defective or non-conforming items in the population. So you can be inspecting maybe hundreds or thousands of units, and you're looking at the non-conforming or defected items. You can be looking at hundreds or thousands of students, and you are looking at the number of failing students, for example. X represents the number of non-conforming items found in a random sample of n items. So we now know that these are the basic characteristics of the binomial distribution. We also have a good idea about the shape of the distribution. In a binomial experiment, there are n identical trials. Just like we started by demonstrating how the binomial distribution is constructed from tossing a coin twice, we can see that tossing coins is an experiment that involves identical trials. Every time you toss the coin, you do it the same way. Same thing in practice. In order to use the binomial distributions, the trials conducted in the experiment have to be identical. In other words, the given experiment is repeated n times, where n is a positive integer. So if we are inspecting, every time we do the inspection, it will have to be exactly the same time as before. Now, each trial will have two and only two outcomes: success or failure, pass or fail, head or tail. So these are basic characteristics of the binomial distribution. We know the probability of success is p, and the probability of failure is 1 minus p, since the sum of probabilities is 1, or we can use the symbol q, which is also 1 minus p, to indicate the probability of failure. Binomial trials are independent, so no trial will affect the trial before or the trial after. This means that the outcome of one trial does not by any means influence the outcome of any other trials. The shape of the binomial distribution will depend strictly on the values of n and p. As n increases, as you inspect more units, the shape will be very much symmetrical, like you see here. Also, if P is equal 1/2, the distribution will also be symmetrical. We've seen that in the example of tossing a coin twice. Here is a case of a binomial distribution, and again, you can think of these bars as being lines, not bars. And here is the x and here is the px. This is a binomial distribution for n equal 5 and p is equal 0.2. Now, if we increase n, meaning going from n equal 5 to n equal 50, you can see that the distribution has become more or less symmetrical by comparison with the original distribution. Also, if I can use the same numbers or the same sample sizes, but for a probability of 1/2, like these cases here, you will see that the distribution is always symmetrical. So the two conditions to have a symmetrical binomial distributions are when n increases, that's very large sample size or number of units inspected, and when p is 1/2. Keep in mind that n and p are again the key or the two parameters of the binomial distribution. Let's take an example. A garment manufacturing process produces thousands of shirts per day. On average, 1% of the shirts do not conform to first quality specifications, meaning we have a 1% defects. Every day, the manufacturer selects a random sample of 500 shirts and classifies through inspection each shirt in the sample as conforming or non-conforming, good or bad. Now, if we let x be the random variable representing the number of non-conforming items in the sample, we can construct a binomial distribution of the variable. How? Here is how. First of all, we need to symbolize a binomial distribution using this universal symbol. And what this symbol said is said that x can be approximated by a binomial distribution. So the variable x, which in this case is the number of non-conforming shirts, can be expressed by or illustrated or simulated by a binomial distribution of the parameters n and p, which are the key parameters. Now, in this case, the parameter n is 500 because that's what we inspect, and the parameter b is 0.01 or 1%. So we are given the parameters. And because of that, we can determine p, and we also can determine q, or 1 minus p. So we have a p of 0.01 and q of 0.99, and we have n being 500. So we have all what it takes to construct a binomial distribution. Again, here is the binomial function. We have nx, p to the power x, q to the power n minus x, n is 500, x is variable, it can change to 0, to 1, 2, and so on. P is 0.01 to the power x, q is 0.99 to the power n minus x, or 500 minus x. We are now ready to construct a binomial distribution. And the way we do that, you can see here. We can substitute x equals 0 in the binomial function, and then we substitute x equal 1 in the binomial function, and so on. So at different values of x, we can generate this term here. At x equals 0, for example, we have 500 combination 0, probability 0.01 to the power 0, q to the power n minus 0, or 500 minus 0. At x equal 1, which is the second term, 501, 0.01 to the power 1, 0.99 to the power x, n minus x, or 500 minus 1, which is 499, and so on. And at the end, if we can resolve each term, we now have the corresponding probabilities for the different values of x. So at x equals 0, we have this value, and at x equal 1, we have this value, at x equal 2, we have this value, and so on. Now we can construct the distribution. Why? Because I have the x values 0, 1, 2, 3, 4, and so on, and I also have the p value coming from this calculations here, meaning that at 0 I have 0.0066, at 1 I have 0.0332, at 2 I have 0.0836, and so on. So that is how we construct a binomial distribution theoretically, given the values of n and p. Later on, we're going to show you how to do that in a short period of time using Excel analysis. Here is another example. If 15% of the pulse produced by a machine are defective, that's a probability, and it's quite a high probability. 15% is a probability of 0.15. The question is, what is the probability that out of 3 bolts selected at random, 0 bolt will be defective? 1 bolt will be defective. Less than 2 bolts will be defective. So these are 3 questions that we have to address. And once again, we are given N, we are given P, and from P we can calculate Q, which is 1 minus P, and we are ready to do the calculations. Now here is the binomial function, and the first question is, what is the probability that out of 3 bolts selected at random, 0 will be defective? So out of 3, we have 0. That is the probability of x equals 0. So the probability at x equals 0 is 3 combination 0, the probability 0.15 to the power 0, times q, or 1 minus p to the power n minus x, or 3 minus 0, which is 3. So that's the probability. So now we have a probability of 0.614 that 0 defect will be out of the 3 bolts that we inspect, or almost a 61% chance. If we're talking about the chance of 1 defect, then we have n is still 3, x will be 1, and following the function we have up 0.325. If you're talking about an x less than 2, well, x less than 2 means either 0 or 1. And since these are mutually exclusive events, since we can add up these probabilities, so we have b at x equals 0 plus b at x equal 1, that sum of these 2 probabilities, which you already calculated, will give us the probability at x less than 2. You can see that either from the distribution or from basic calculations of each probability term, we can find the probabilities associated with the binomial distribution. Again, if we can construct the histogram or the binomial distribution, and we can calculate mu and sigma square. Here is mu equal np. Now notice that n is 3 and p is 0.15. So the average is 0.45. That is the average of the x values. Now you know that the x values are discrete. They can only be 0, 1, 2, 3, 4. But the average itself can be a fraction, as you can see. The variance is NPQ, so now we have the mean and the variance. Let us now see how we can find these values on the Excel spreadsheet. So we need to be ready to go to Excel. But before we do that, we're going to go to the slides and go over how we do the Excel analysis quickly to determine the probability value associated with the binomial distribution. Let's go to the slides. Using Microsoft Excel to perform binomial distribution analysis. Well, in Excel, you have the function fx, which we used before to calculate the average and the range and the standard deviation. Now, if we click on the function, but first we need to know the parameters of the binomial distribution we are dealing with. In this case, let's use the example where p was 0.15 and the q is 0.85. Keep in mind that the n in this case was 3. And suppose that the questions are to find the probability that x equals x 0, or the probability at x equal 1, or the probability at x less than 2. Well, after you click on function, then you need to go to select a category which is statistical. So we go to function and select statistical. And we go specifically to binomdist, that's binomial distribution. And we click on this and we say go, and when we do that, it will give us a menu that allows us to solve all these problems. Now, in the first window of this menu, we have the numbers. Notice that we're talking about probability at x equals 0. So that is the x value. The second window is the n value. We have an n equal 3. And the third one is the probability, which is 0.15. So we have all what it takes to calculate. We have the x value, we have the number of trials, and we have the probability 0.15. And if we can do that, then we almost have reached the answer to probability of x at x equals 0 from a binomial distribution. Now notice here we have a window that's set cumulative. Now cumulative can either be false or true. False if you want to get the exact probability, which is this case probability at x equals 0 or probability at x equal 1. True if you want to get cumulative probability, such as this case here, probability of x less than 2. So for this example here, if we type these values, you will immediately see the probability at x equals 0. If you click OK, you will also see it in the spreadsheet as you can see here. So the x, the n, and the p are the key, and we select the false in case we need the exact probability. Here is for this example of p at x equals 0. And this is exactly the value that you will get if you do the calculation manually as we did before. Here is the example at x equal 1. Notice x here is 1 now, n is still 3, p is 0.15, and we put false here because we get in the probability at x equal exactly 1. And we click OK, we can see the probability, and that will give us a value that's equal to the value we obtained before. Now if we want p at x equal less than 2, or at x less than 2, that is x0 plus x at p at x equals 0 plus p at x equal 1. So we just obtain these two values. We can add them up, and that will give us the value. Or we can go to Excel, and now that we have the probability of x less than 2, then we're really looking at what's less than 2. It is 1 or 0. So that's why we put x here as 1. That doesn't imply exactly 1, because you notice here this is 1, n is still 3, p is 0.15, but now we have, instead of false, we have true. So true means 1 or less. So that will give us the probability of the event at x less than 2, and that is the cumulative probability up to 1, or p at x equals 0 plus p at x equal 1. And you can see the value here correspond to the value that we calculated early on. This session, as you can see, we have gone through the binomial function, the basic characteristics of the binomial distribution. We were able to see how the distribution is constructed theoretically, given the two parameters of the binomial distribution, the n and p, and of course varying the value of x, which will have to be discrete. And we went to Excel to show you how you can obtain the different probability values using Excel function. In practice, people use the binomial distributions for many applications. As we mentioned, it's used for most discrete variables. Defects, returns, number of failing students, number of events of some form, pass and failure, stop and go, accept, reject, yes and no. These types of variables that are described in that fashion, or actually number of defects, number of returns. All of these are used in the context of binomial distribution. If you can construct a binomial distribution describing these variables, then you very much can analyze it, and you can obtain a lot of information about the chance of some specific events to occur. For example, what's the chance of having 2 or more defects in a shipment? What's the chance of having 5 or more students failing a class? And so on. So these are very important applications. We're now about to start another this probability distribution of discrete variable. which is the so-called Poisson distribution. The Poisson distribution is very, very unique. It typically models values or variables that are rare in nature. They do not occur very often. The chance of something, the chance of, God forbid, an air crash, for example, or the chance of having a brand new machine that will produce defects. Or, a brand new machine should not be, or is not expected to produce so many defects. The chance of a brand new TV to have a malfunction. The chance of a new laptop or a new computer to go bad in the first 1 or 2 days of using it. These are events or variables that we wish or we desire for it to be rare. We desire for it not to occur very often. In this case, the Poisson distribution is more suitable for these types of events. Another interesting thing about the Poisson distribution is that if you ever analyze a set of data and you find that the mean value is exactly identical to the variance or close to the variance, then you will know that you are dealing with a Poisson type variable or a Poisson data. With this introduction, let us go to the Poisson distribution and see how it is described and how we can use it in real applications. If you notice in this picture here, again, this is a familiar, at least by now, probability distribution. And it is discrete because we have lines instead of bars. And here are the x values, and this is the probability. But you also need to notice that there is a heavy frequency or heavy probability at the low values of x. So if this is 0 or 1, then we see that we here have the highest frequency. And that's what I meant by that the Poisson distribution best models rare events or events in which the probability of 0 or 1 defects is the highest, while the probability of high number of defects is very slim to none. You can see also the exponential trend of the Poisson distribution, which will be reflected in the Poisson function. In fact, here is a Poisson function. Probability of x is lambda to the power x, e to the power minus lambda, divided by factorial x. And if you look at here, what you see is that the Poisson function only have one single parameter, which is lambda. Okay? Because once you know lambda, then you can easily change the values of x and construct the entire Poisson distribution. Now, the values of x has to be discrete, 0, 1, 2, 3, 4, just like the binomial distribution. But the key feature here is that we only need a single parameter, which is lambda, to fully describe a Poisson distribution. Indeed, the mean of a Poisson distribution is equal lambda, which, if you recall, in the binomial, it's equal np. And the variance of a Poisson distribution, as I mentioned in the introduction, is also equal lambda. That's what I meant by the mean and the variance are identical, and it's equal np by comparison with the binomial. Having said that, it's very important that we define lambda. Lambda is the number of defects or failures per unit. Okay? And that's very important. Of course, we know what's E, but the parameter of the Poisson distribution is lambda. And it's the expected average events per unit. And that's very important. Anytime that you have to deal with a parameter that's expressed per unit, then you need to think of a Poisson distribution. We will see that by example very shortly. Here it is. The mean number of accidents on the job per month at a certain company is 3. So this company is looking at accidents per month. Sometimes they see 0 excellence. Sometimes they see 4, sometimes they see 2, sometimes they see 3, sometimes they see 2 or 1. But over a certain period of time, over many months, they find that the mean number of excellence per month is 3. If we want to model this using a Poisson distribution, then we have all what we need, because 3 is actually the lambda. It is the expected average of events, in this case excellence, per unit, and the unit in this case is months. So lambda is 3, and that's all what we need. I can do exactly what I did with the Poisson with the binomial distribution. At x equals 0, I can calculate p0. Remember, the function is lambda to the power x e to the power minus lambda divided by factorial x. So in this case, at x equals 0, lambda is 3 to the power 0, e to the power minus lambda, that's minus 3, divided by factorial 0, which is 1. At x equal 1, we repeat the calculation. 3 to the power 1, e to the power minus 3, divided by factorial 1, and so on. We have the probability at different values of x, and by doing so, we were able to construct the Poisson distribution. Now, this is lambda equals 3, and this is quite high. And one thing we need to know is lambda should be smaller than that. Otherwise, we are basically dealing with another type of binomial distribution. In fact, if you have 3 excellence per month, then a binomial distribution would be more suitable. But later on, we're going to see examples of real Poisson distributions. You can see that the different terms that we calculated can be illustrated in the graph as bars or needles. Here, we're talking needles because we have discrete values. The mean is 3 because that the mean equal lambda, and the variance is 3, meaning that the standard deviation is the square root of 3. Suppose we want to determine the probability that in any given month 4 accidents will occur at the company. Now, keep in mind that the average number of accidents per month is 3. So if you want to determine the probability or the chance that at a random month or any given month 4 accidents will occur, we will have to use the Poisson function. That's p at x equal 4. Meaning we're going to have to put lambda equals 3, x equal 4, e to the power minus lambda or minus 3 divided by factorial 4, and that gives us 0.168. Meaning we have a probability of 0.168 that a random month may have 4 accidents, or we have a 16% chance, almost 17% of having an accident, 4 accidents in a month. That could be serious in any organization. Here is another example. If the number of some type of metal defects is assumed to follow a Poisson distribution with a mean value of 1. Now that's more like a Poisson distribution. The mean value or lambda is 1 per 1,000 square yard. You notice the sample space here is large, and only one defects or metal defects is shown or expected. So what's the probability of finding 2 defects? Or finding at most 2 defects, or at least 1 defect? We can do any one of these probabilities using the Poisson function. We know that lambda is 1, so if you want to find the probability of finding exact 2 defects, then it's easy. At x equal 2, we can easily substitute for x by 2. We have lambda equal 1, e to the power minus lambda, and divided by the factorial 2, and here is the value of the probability at x equal 2. If we want to say at most 2 defects, at most means it can be 2 or less. So in this case, we have 2, and we have 1, and we have 0. So we can find the Poisson function for each one of these at 0, at 1, at 2, and all what we do really, lambda is the same at 1, but we substitute in for the values of x being 0 at one case, 1 in the second, 2 in the third. And that gives us the probability of at x less than or equal 2. If we are looking at least 1 defect, that means it could be greater than or equal 1. So greater than 1 could be 2, 3, 4, and you can go to infinity. Well, in this case, we have to use the complementary probability. That is, the probability of x greater than or equal 1 will be equal to 1 minus the probability at x less than 1. The reason for that, it's easier to get the probability at x equal less than 1, which is basically the probability at x equals 0. So we know the probability at x equals 0, we subtract that from 1, and that will give us the probability at x greater than or equal 1. These are the different ways of using the Poisson distribution solving problems. In Excel, we can do these calculations very quickly, just like we did with the binomial distribution. Let us see how we do that using Excel functions. Here is the Excel function. So if we click on Excel function and click on select a category as statistical, just like we did with the binomial, but this time we're going to go to the Poisson. And if we click OK, then we are about to calculate any probability term that follows a Poisson distribution. Here again, keep in mind that the Poisson needs lambda only. So we have the x value here. That's if I want to get the probability at x equal 2. And we have lambda here, which is 1, remember, for the last example we had. And you also should remember that when we put false here in the cumulative, we are talking about the exact probability, meaning we're going to get the probability at x equal 2. And here it is, 0.1839. So we follow the exact procedure that we did with the binomial distribution in order to get the probabilities following the Poisson distribution. So what we get in here is equivalent to P at x equal 2. It's equivalent to doing the calculations manually. And as you can see here, it is the same value obtained real quickly. If I want to get the probability of x less than or equal to, which involves 1, 2, 3 terms, x equals 0, x equal 1, x equal 2, then in this case, less than or equal to, we know what to do with the Excel function now. We know if we put x equal 2 here, okay, that will give us the 2 or less. The lambda is still 1, and we use this time true, not false, because we are about to get cumulative Poisson probability, not the exact Poisson probability. So this is how we get the x less than 2, less than or equal to. If I want a probability of x greater than 1, then this is one term, which is the probability of x equal 1, x equals 0, minus 1. I can get that using the previous procedure, or I can go and put x equals 0, lambda equal 1, and now I have the probability at x equals 0. I can take that minus 1 and get the value of the probability at x greater than or equal 1. The point here is we can use Microsoft Excel to calculate the probabilities associated with a binomial distribution or a Poisson distribution. If that's your choice, so be it, especially if you are doing too many analysis. But if you are doing few analysis, I believe these calculations can be done easily manually. But Excel provides another option.
Video course on statistics. From basics to advanced subjects. Dr. Yahya El-Maghazi, Professor Emeritus at Auburn University, Alabama, USA. Former Dean of Science, Technology, Math, Engineering at Ocean County College, New Jersey. A visiting professor at a number of universities including Rowan University, Keene University, and Montclair University, New Jersey, USA.